He researched highly unsaturated hydrocarbon molecules of astrophysical relevance. So then Tim returned to Australia in 2003 to take up a position at CSIRO, researching artificial photosynthesis, and he was appointed to as a lecturer in the School of Chemistry at the University of Sydney in 2004. He rose through the ranks to associate professor before moving to UNSW in 2014 as a professor and an ARC, that's the Australian Research Council, future fellow. So at UNSW, he was research director of School of Chemistry and chief investigator of another ARC Center of Excellence in Exciton Science. And Tim has been the recipient of a number of awards, including the Koblenz Award in 2010 for contributions to the science of molecular spectroscopy, and another award recently, which I'm not supposed to say. Anyway, so Tim, if you'd like to share your screen now and give us a 5-minute.
Yeah, no worries, and thanks for the pleasant introduction, Albert, who I might add is has just been awarded a future fellowship himself from the Australian Research Council. Okay, so you can see my screen. Yep. Okay, so I am, just as a disclaimer here, I'm a spectroscopist. I am this strange creature that is somewhere in between being a chemist and being a physicist. And everything we know about the chemistry of space comes from spectroscopy, right? And spectroscopy, hand in hand with quantum physics, right, has led to our deep and profound understanding of molecules in general. So the topic of astrochemistry really concerns the chemical transformations of matter within the interstellar medium and in and around stars. And I really like this this diagram that was produced by Sun Kwok at Hong Kong University, because it sums up why we do what we do and what the big picture is. So this series of seminars is about prebiotic chemistry, and this shows you how astrochemistry relates to prebiotic and then actual biotic chemistry. So it's a lovely diagram, right, showing you the stuff that Albert works on in the bottom right, which is origins of life, strange creatures lying around in ponds and climbing out. But astrochemistry, of course, occurs out there in space. And what we've got there is the cycling of matter through the interstellar medium following the life cycle of stars. So carbon atoms, which are the most interesting atoms there are, right, are formed in main sequence stars, and then as those stars die their deaths by whatever means, be it through forming a planetary nebula or going supernova, they eject the building blocks of chemistry into outer space. Now, if it happens gently, then chemistry starts to happen in the dense circumstellar shells and then wafts off into the diffuse interstellar medium, from which it is then incorporated into dense clouds where more chemistry happens, and we're going to be hearing about that. And then, of course, into star and necessarily planet formation. And it's on those planets that we believe that life evolves, and it evolves from the inventory of chemicals available to it, which is delivered from space. So how do we know what's out there is all comes down to spectroscopy. So I'll just paint a few little pictures, and not stepping on Samantha's toes at all, because she's going to tell you a story about complex organics. But in my world, I'm more interested in optical spectroscopy, and because of that, I'm looking at large aromatic chromophores. And what comes with that is all of the studies relating to large organic molecules surrounding stars, and both in their birth and in their death. And when you look in the infrared spectra of stars that are undergoing a slow death, or even in formation regions where there is a hot illumination source, you see infrared emission bands, which are characteristic of aromatic species. But because they're characteristic of just about all aromatic species, we don't get specific chemical identities here. So these bands are together these days called the aromatic infrared bands. Historically, they were the unidentified infrared bands, but they're thought to be due to structures something like this cartoon below, which is largely aromatic. It's got a lot of sp2 hybridized atoms with hydrogens. It's got aliphatic groups and it's got heteroatoms. And a beautiful example of an object that shows up these bands is the red rectangle shown at the bottom right, which is a protoplanetary nebula being viewed side on, so that the central object is occluded by a very dense dusty torus. Now, until only a short time ago, no specific PAH had actually been confirmed in the interstellar medium. But this shows you on this slide the great power of radio astronomy to identify specific aromatic or specific molecules. So this beautiful work by Maguire and building on decades of work now by McCarthy shows the detection of the first two specific polycyclic aromatic hydrocarbons in the interstellar medium. And you'll notice that they incorporate nitrogen atoms. So this is a 1-cyanonaphthalene, 2-cyanonaphthalene. And that's necessary in this case to provide a radio handle so that it's got a dipole moment to be observed. But it is found that these specific PAHs they're observed at maybe an order of magnitude greater abundance than what's expected due to by the astrochemical models. And that highlights the fact that astrochemistry is an evolving field, and the theory of astrochemistry is necessarily constrained by observation. I've got just a picture here at the bottom right of Kelvin Lee, just because he was a graduate of our laboratories here at UNSW. I took this picture off Samantha's website to try to join what I'm talking about to her. She's going to be talking about these complex organics shown at the bottom left, that sort of thing, which do not have an optical chromophore, but are still necessarily very interesting, especially in relation to origins of life. Now, in circumstellar shells, you also see things as complicated or beautiful as buckyballs, as well as random aromatics and specific aromatics. And just to highlight, how little we really know about the life cycle of carbon in space, if we really understood where what carbon did in between the death of a star and the incorporation into another star system, then we would absolutely know the identity of the diffuse interstellar bands, which are a series of absorption lines seen in the interstellar medium. But there is only one species which is positively so far identified with a DOB, and that is C60 plus. Right, so this field is wide open, it's evolving, and it's very exciting. And just in closing, I just want to show that the next generation of astrochemists are already being trained. If you go to your local bookshop, you can buy this book, Astrophysics for Babies, and open it up, and you'll find that the story of that book is actually the story of astrochemistry and the life cycle of carbon in space. And it finishes off this lovely little book by showing how these carbon atoms are incorporated into life forms on Earth. Well, the main show is Samantha, so I'm going to stop talking and let us get on with things.
All right. Hey, thanks a lot for that super interesting talk, Tim. Now I know what I can buy my nieces for Christmas. Excellent. So Samantha, if you'd like to get set up, I'll go ahead and give you an introduction here. So Samantha Scibelli is a PhD candidate. I hope I said your last name right. And a
Yes.
National Science, very good, and a National Science Foundation graduate research fellow who studies astronomy and astrophysics at the University of Arizona's Department of Astronomy and Steward Observatory. She received her bachelor's degree in physics and astronomy in 2017 from Stony Brook University. And Samantha studies dense nurseries of gas and dust prior to the formation of stars in order to understand their evolution and complex chemistry. Samantha is interested in the broader topics of star formation, astrochemistry, astrobiology, and radiochemistry. So Samantha, if you're ready, please go ahead and take it away.
Yeah, can everybody see my screen and hear me okay?
All good on my end.
All right, awesome. Well, thank you for that introduction, and Tim for giving a great intro that makes my job easier here, talking to all of you about the research that I do at the University of Arizona. As mentioned, and as this picture of me by a telescope suggests, I am a radio astronomer. So I use radio telescopes to study molecules in space. And since I know that we are at a seminar that kind of has a mix of interdisciplinary studies, I thought I'd kind of start broad and go in. First of all, the types of objects that I study specifically are dense cores of gas and dust that will form sun-like stars. So this is an example of a prototypical kind of starless core, B68. And in the visible light, it looks like a silhouette, like there's nothing there, you know, that there's these voids in space. However, we know this is not true. If we put our radio eyes on and look at this object instead with radio light, we know that these objects are filled with dense molecular gas, which we then, you know, can probe with our radio telescopes. And one of the interesting things too about being at Arizona, particularly, is that the molecular astronomy actually began at Arizona at Kitt Peak, not with the same telescope that I use. It was actually a different telescope, but same site, back in 1973 with the discovery of CO towards a dense star-forming region. And as mentioned, right, the great thing about radio astronomy and molecular spectroscopy is because of quantum mechanics, you know, we know exactly the frequency and the wavelength that a certain molecule will emit at. So for example, for the CO molecule, we know exactly at 115 gigahertz, if that molecule is present, we should see a spike in the line. And indeed, in this first discovery, they detected CO. And this kind of began the hunt for other molecules. And we know now that there have been a lot of other molecules besides just CO detected in space. And that number is actually around 270 molecules now. This paper, or this list, is actually outdated even from a year or two ago. And most of the molecules that have been detected in space have been done so by radio astronomy. And the types of molecules that I'm interested, as has been alluded to, are what are considered complex organic molecules. So if you're a biologist or chemist listening, you might say that this is crazy to consider a complex molecule any atom with 6 or more atoms and at least 1 carbon atom, which is what we define it as astronomers. But to us astronomers, these are complex. And we believe that they are, you know, important because they are not, you know, signs of life, but they are the precursor molecules necessary for prebiotic chemistry, right? And so since we cannot go out and observe yet the organic matter directly in space, we use our radio telescopes to get signatures of these molecules that are the precursors to the precursors of things like DNA and RNA. And so we can ask big questions that are interesting to astronomers, astrochemists, astrobiologists, such as trying to understand if the organic molecules synthesized in space, if they contribute to the chemical evolution needed for the emergence of life on Earth. And so I will argue that I think one of the more interesting places to search for these complex organics is in low mass star formation, where you will form sun-like stars and planets. And so here is our typical picture of the star formation process for low mass stars. You start out with a molecular cloud of gas and dust. Filamentary structure forms, and within these filaments, you have starless cores, which I study and we'll talk about later on. And then you also have prestellar cores, which I also talk about. The distinction there is just prestellar is considered to be a core that is gravitationally bound or pressure bound and will, form a star. It's kind of the next stage in evolution. And then once a baby star or protostar is turned on, this is what's considered a protostar, where you have jets and outflows and an accretion disk. And then you'll get a protoplanetary disk, which people believe in the gaps in these disks, you have planets forming. And then eventually you'll have a mature planetary system with sun-like star, planets, comets, etc. So it's really important to try to understand how solar type stars evolve if we want to understand how chemistry, right, evolves from the earliest stages to the later stages, and to also try to understand what type of chemical inheritance gets passed on from stage to stage. And what's interesting too is that in each of these stages, COMs, or complex organics, have been detected. So I'll give some examples of that to kind of show detections. For example, comets have been known to have lots of complex organics detected. Here, each column is a different complex organic detection spectra, and each row is a different comet. And in addition to comets, right, moons in our own solar system show complex chemistry. In Titan's atmosphere specifically, there's this molecule vinyl cyanide, which people think is important if you have nitrogen rich places, maybe nitrogen bearing species life. And it's important for forming cell-like membranes, and if you have liquid methane oceans, which Titan does. Even in the protoplanetary disk stage, so here, for those maybe not familiar, but this is an image maybe you've seen from ALMA observations. So this is a big radio interferometer in Chile, took this really nice image of this protoplanetary disk forming, again, where the gaps represent where planets might be forming. And in this disk, they detected methanol, which is a more simple complex organic. And then even this year, more recently, we're starting to go to higher levels of complexity. Dimethyl ether, which is the largest molecule found at this stage of planet formation, was detected in a disk. And also in protostars, in earlier stage, there's lots of complex chemistry. This is IRAS 16293, which has had many surveys towards it, searching for complex organics. This is a map of glycoaldehyde. And to kind of tie this together a bit more with the astrobiology, because people have been trying to connect this more to astrobiology and to prebiotic chemistry. Astrobiologists have been trying to work with this RNA world scenario. So this complicated figure, you just have to take away that each box is a molecule in this RNA world scenario, which suggests that early life form relied solely on RNA to store genetic information and to catalyze chemical reactions. And what I want you to take away is that each box that has a solid outline is a molecule that has been detected in space and is a part of this, chemical scheme. And glycoaldehyde is one of them, one of these precursor prebiotic molecules important for forming RNA and larger molecules in this chemical scheme. And so great, so we've seen, these chemicals in these different stages, but do these larger molecules that we're detecting, is there evidence that these molecules are inherited and will survive the star formation process into later stages, or survive from earlier stages even? And astrochemists believe that actually there is evidence to suggest that these molecules are sticking around. This is a famous plot that a lot of astrochemists like to show. Again, this is that same protostar, this 16293, versus the comet 67P. And what it's showing is abundances of different COMs with respect to methanol for both of these objects. And you see that there's a tight correlation in both. And this is also, not only are there correlations and abundance between these two objects in later stage star formation, but this suggests that these molecules are sticking around and could be inherited from the pre-stellar core phase. And so this is kind of motivation then as to why studying an even earlier phase in the cold molecular gas and dust, even before a protostar is turned on, is an important stage to look for these complex organic molecules, because they can give us a better idea or constraints on initial chemical conditions. Another reason why studying complex organics at earlier stages of star formation is because of the to try to understand the chemical processes and formation mechanisms. In protostars, we know relatively well, because there's an internal radiation source, gas phase chemistry can drive, molecule formation. However, right, in the pre-stellar and starless cores that I'm going to be talking about, these are very cold and dense regions. And so understanding why some of these complex organics are prevalent is still not fully understood. And so we really want to understand how prevalent these large molecules are in these dense environments to try to get a better grasp also on formation mechanisms of these molecules. One of the things hindering our understanding of complex molecule formation in cores is that up until surveys that I've done, which I'll talk about in the next slides, only a handful of very well-known, dense, and evolved pre-stellar cores have had higher complexity organics observed towards them, such as this L1544. And so here, coming back to kind of our inventory of complex organic molecules in different objects is kind of a summary plot that I'll keep coming back to. On the y-axis, you have abundance, again, of different COMs with respect to methanol for different objects. So in the yellow region, we have dense starless cores. In the blue region, we have protostars, and in pink, we have comets. And you again can see this trend in abundance through different stages of low mass star formation. But in the dense starless core region of the plot, we really only have data points for very evolved cores that have had higher complexity observed towards them. So what about for complex organics, earlier in more of the starless core phase? Can we still see a high level of complexity? So this leads then to my first, one of the first surveys that I did with the Arizona Radio 12 meter. We decided to search for complex organic molecules in one particular core. This is core L1521E. It's in the Taurus molecular cloud. Compared to other cores that had been previously targeted, such as L1544, it has very low CO depletion, so CO has not frozen out in the center, which it's known to do for more evolved and dense cores, and it is no indication of collapse from its velocity structure. So we decided to search for different complex organics, and we detected a lot. So here's a summary table of all the molecules that we searched for and detected in different transitions of those molecules. So, dimethyl ether was detected in this object, which is that same molecule, right, that was detected in that protoplanetary disk. Vinyl cyanide, which is that molecule that's important in Titan's atmosphere, was detected. So this is, telling us that we're detecting a prevalence of these complex organic molecules millions of years earlier than even in L1544, which is that very evolved core. So we're detecting these molecules earlier than previously thought. And now that we have line observations, one of the interesting results that I'll go through is that we wanted to try to compare the abundances that we get from our measurements to chemical models. So in this graphic on the left, it shows different types of chemical, complex chemistry for cold cores. I'll focus just for now on this mechanism called reactive chemical desorption, which basically you have radical type molecules forming on the grains. Those get desorbed off by chemical reactive desorption, form in neutral gas phase reactions to form the larger complex organics. And so models such as this one on the right have been produced to try to explain abundances in these cold cores. So what this plot is showing is abundance of with respect to hydrogen on the y-axis versus time in years. And I've highlighted in pink dimethyl ether and showing that for core L1544 and for another evolved core L1689b, the modeled abundance does a pretty good job of reproducing the observed abundance. So we wanted to see if we could also use the chemical reactive desorption chemical pathways and this model to try to reproduce abundances for our low CO depleted core L1521. So here are the results. And as you can see, we were not successful. So again, this is the same plot showing abundance with respect to H2 on the y-axis versus time in years. And the model are the curves and the horizontal lines are the observations. And so because L1521E is a lot lower density, has low degree of CO freeze out, so there's more CO in the gas, to react with things, and more, right. And so the complex organic molecules are being destroyed and we're under predicting our abundances, as you can see here. And so this is telling us that gas phase chemistry and reactive desorption alone are not sufficient to explain the observed abundances in starless cores. And so this is something to be looked into for future work to try to explain the abundances in these lower density starless cores. Okay, so coming back to our kind of summary plot, we've now added to the younger portion of this plot complex organic molecule detections for L1521E. So that's great, we've added to this, but it still leaves me with questions because again, there's only 5.5 cores on this diagram, and we know that there are a lot more protostars and more protostars that will be surveyed with ALMA upcoming that will look at complex organics. So it would be great to know if complex organics are prevalent in a more representative sample of cold cores. If are complex organics, are we just looking at famous cores and particular cores that might have this complex chemistry happening? What about in a random kind of sample of cores? Do we still see a prevalence of COMs? So this leads then to another survey that I did as part of my thesis work. Instead of doing a line survey, I did a core survey of 31 cores, also in the Taurus molecular cloud. So you can see in this map, it's adjacent to L1521E, the core I just talked about. These 31 cores along the filament, we targeted each again with the Arizona Radio Observatory 12 meter to search for methanol, kind of this mother molecule of COMs, and then the next level of complexity, acetaldehyde. I won't be able to get into all the nitty-gritty details. If you're interested in, I've left a QR of the paper here, but I'll just kind of go over the main results. we detect a prevalence of complex organics. So methanol was detected in all of the pores, and acetaldehyde was detected in 70% of the pores targeted. So great. Now we can add to our summary plot again, and we've significantly increased the sample size of starless and prestellar pores that have higher level complexity columns detected towards them, higher than methanol. And when we plot this on our comparison plot of abundance versus methanol through different stages of low mass star formation, we again see a similar trend in abundance throughout the different stages of star formation. And this is again supporting the idea that at least some of the complex species that are in the dense starless and prestellar pore phase are being inherited to the later stages of star and planet formation. Okay, so that is kind of work that I've already done in the first part of my thesis. Now I kind of want to talk about a new program in the last portion of my talk. I'm currently leading as PI a survey called Glucose. If you're an astronomer, you by law have to have a acronym for your survey, but it stands for the GBT L1544 Unbiased Complex Organic Survey. So as the name suggests, we're now looking at the more evolved portion of this graph in L1544, because one reason to look for, test the limits of chemical complexity in this core is because it is evolved and will form a star relatively soon. So if we want to trace the chemistry into later stages of star formation, this is a good core to target. Kind of zooming back in to give you a full picture of what I've been looking at so far in the Taurus molecular cloud. L1544 is up here. Another reason it's good to study is because they're already detailed physical and chemical models, right? As I've shown before, there's these chemical models that do a pretty good job of reproducing abundances. There's detailed physical models of these pores. And so that's another reason why L1544 is a good target to study. It's in this same molecular cloud where we have L1521E, which was that core, again, that I did the large line survey of. That's a very young starless core. And then the L1495 filament, which I did the core survey in. And I'll also go on a bit of a tangent to say, while I won't be talking about this work in this talk, since we're focused more on chemistry, soon L1544 will no longer be one of the only prestellar pores that have detailed models. For the last phase of my thesis, I have been working on doing dust radiative transfer modeling of the pores in that L1495 filament. So with these physical models, we'll be able to create then future chemical models with wide ranges of densities and temperature profiles in order to really pin down chemical formation mechanisms and to do some chemical modeling. So this is a subject of future work or something I would hope to do in my postdoc. But for now, let's get back to L1544 since it is already well-studied, well-known core. It is the target, again, of the survey. So I'll give you kind of some overview facts. As the name also suggests, we use the GBT, which is a 100-meter radio dish in West Virginia. And this survey will target L1544 in a 10 gigahertz unbiased range of the spectrum from 38 to 48 gigahertz. This is a large legacy program there's more than 600 hours on this telescope. In fact, I have observations tonight that start in a few hours. So we keep collecting data as the time goes on. But I'll show some preliminary results of kind of what we expect to do with these data. in this window, there are actually many energetically favorable comms, more so than, say, at higher frequencies, like around 90-ish gigahertz, which is the frequency that I use to look for comms from my previous work. And there's also very other interesting molecules like carbon chains, different isotope species, and deuterated species that haven't been detected yet. Here, for example, is synthetic spectra that I use to predict line strengths within our survey frequency range. And already you can see that we're detecting bright complex organic molecules. For example, this is acetaldehyde being detected at 115 millikelvin brightness. And just to give you a perspective, this is about like 4 to 5 times brighter than the brightest line that was detected in the 3 millimeter band. And also we see bright vinyl cyanide lines, which is the one here. So this will be great to constrain complex organic molecule abundances, which will then help with chemical modeling and things like that. And additionally, I'll highlight as well, one of the interesting things too that we can do with this survey is do follow-up observations. So ALMA, which is that interferometer in Chile, it will a new band will come online that covers basically the same window that our glucose survey is conducting. And we'll be able to target the bright lines that we discover and detect in glucose with ALMA to really probe the spatial distribution of these complex organics, which hasn't been done before for higher complexity comms to good sensitivity. So this will be something that can come from the glucose survey as well. And another thing that might be more interesting to a wider range of people and astronomers and chemists and things like that is that the GBT has a uniquely high spectral resolution and will be able to do detailed chemical and kinematic velocity studies to probe these bright lines, but also comms towards L1544. And these data will also produce a rich data set. And so people can publicly use the data when it's released and can lead to a lot of other interesting studies. And we're connected also, Brett McGuire, who Tim talked about, that found the polycyclic hydrocarbons. The Gotham team, they have been helping with the glucose team to run the data through their pipeline. And I was told from Brett that the resolution of the GBT is good enough that actually some of the molecular lines that we detect in our surveys are at more precise frequency than even what some laboratory studies have done. So it'd be interesting to kind of follow up on what has been detected with our survey and maybe some laboratory experiments as well. So lots of interesting stuff can be done with this survey. So it's still at a very early stage, but stay tuned for more interesting science to come from this. So I'll wrap up on my summary and takeaway slide. So again, one of the first things I did in my PhD was surveys of complex organics, whether it be in the young core L1521E, or doing a large core survey in Taurus, searching for methanol and acetaldehyde in 30+ cores. I didn't go into too much detail since this is a chemistry talk of the dust modeling that I've been doing in the later half of my thesis, but these physical models will really help us pinpoint the conditions needed for chemistry to thrive, and will help provide the models that the physical models that chemical modelers need to try to reproduce complex molecule abundances. And there's a lot of exciting future science with glucose, more complex organics, and other interesting molecules to study. So With that, I will stop and see if there are any questions.
All right. Thank you very much, Samantha, for that incredible talk. It's really amazing how you can actually show organic molecule evolution throughout different stages through star formation. Seems like it's just an incredible amount of work. It's amazing. So at this point, we'll open up the chat for questions. So feel free, if you have any questions for Samantha or Tim, to type your question in the chat or just raise your hand and we'll unmute you. But in the meantime, I have a question. So it seems like in order to be able to detect any molecule in space in particular, it sort of implies there's a huge amount of it, right? Is there any way to quantify, like in terms of mass, like how much of the glycoaldehyde is out there, for example, around a particular protostar?
Yeah, so it's, I would say, probably, well, to us, small amounts because they're on, compared to, say, hydrogen abundances, there are 10 to the negative 12 or 10 to the negative 13 or something like that. So yeah, usually what we do to try to quantify that is you compare your column density that you get along the line of sight from radiative transfer to try to calculate, how much of that molecule that you're seeing, and then you compare it to hydrogen, molecular hydrogen, which there are maps from, say, infrared observations, like Herschel provides column density of molecular hydrogen. So that's a good kind of estimate to try to, see, like how much of this molecule compared to hydrogen there is. And usually, it's a small fraction.
Yeah, I mean, maybe I'm just wondering if it's like you have so much glycoaldehyde, for example, that it's just like covering the early Earth or early planet.
I see.
Many times over. If it all were to like fall on it or something like that.
Yeah, it is a lot. I think, for example, like acetaldehyde, I think would be, enough to like fill like some percentage of our oceans or something like that. If you think about it in terms of that,
It's really fascinating. There's some questions in the chat, so I'll just read them out.
Okay.
So Dave Deemer says, are the organic compound in a gas phase, or are they in the mixed ice on mineral dust particles?
Yeah, that's a great question. So a lot of the organics we're not seeing, actually, because I would say a lot of them are locked up in the grains and ices. So what I detect is in the gas phase with our radio telescopes. But of course, James Webb will be able to try to detect, say, ices of things beyond, say, methanol. I think maybe acetaldehyde, but in like protostars or maybe in dense pores. So there's a lot of interesting work to be done to try to understand what's locked up in the solid phase, because I think there are organic compounds not just in the gas phase, but that's what we can detect with our radio telescopes. And what's nice about the radio telescopes, as Tim also mentioned, is we can actually, because of rotational spectroscopy, we can know exactly which molecule it is, which transition it is, which gives us a better understanding of how much of that molecule there is. So that's, long-winded way of answering your question.
All right, so we have another question from David Appel. You called these organic molecules precursors to precursors of RNA and DNA. Are the second precursor molecules like amino acids? Or
so for example, I like acetaldehyde, I have studied a lot, and that molecule is important for forming, it's been seen to form things like amino acids, I have to look up the exact amino acid that I'm thinking of, but in like carbonaceous chondrites. So I would say that these are the precursors to the precursors because, as you say, I would acetaldehyde in particular, I can think of is important for forming amino acids.
Yeah, and I can just second that. Like aldehydes plus cyanide,
Yeah.
plus some ammonia gives you amino acids. And I guess you're also making hydrogen cyanide as well, or people have detected that.
Yeah. It's interesting because the hydrogen cyanides too are more prevalent in kind of the later stages as well. So it's interesting.
Yeah, very cool. We have another question from Arlie Castillo. So for aspiring astrobiologists, do you suggest any at-home or smaller scale experiments we can do? It's a good question.
Oh, interesting. That's a good question. I mean, what's great about astronomy, especially today, is that there's a lot of things that you can mine in the large quantities of data that have been collected from telescopes. So just speaking, since I'm an astronomer, about the at-home things you can do as an astrobiologist with telescopes, there are archives of, say, ALMA data of objects like protostars. There's, archives of lines that you could go and look for to see if people have missed detections of things. So I always like to start with archival data or things from telescopes, but I don't know if that answers your question.
Yeah. If we have any more questions, feel free to unmute or raise your hand and we can unmute you if that's also what you would like. I thought it was really fascinating how these it seems like the molecules that you observe, like not only do they exist in some abundance, but they also survive, or they seem like they survive for what would the time scale you think would be, like millions, hundreds of millions of years? Like they just kind of are out there.
Yeah, I would say on time scales of millions of years, which in the grand scheme of things for astronomical times, right, it's not that much.
Yeah.
But I mean, a prestellar core though will collapse on the order of like hundreds of thousands of years, so smaller time scale as well. So those are kind of the scales to think about.
Yeah. So I guess like if you were to look at a really evolved star system, like you basically wouldn't see like any of these signatures. Is that right?
So I know that people do look for, there have been detections of complex molecules in evolved stars and in protoplanetary disks. And so the question there is, right, there is a question, right, as if, are these molecules, when are they being formed? And is it from, say, the diffuse cloud phase, being left over from, molecules being ejected from dying evolved stars, and then those kind of last into the prestellar core phase, or are they actually being formed in the prestellar core phase? And there's a few papers that actually show that I think like methanol or I'm forgetting which particular ones, but have actually been detected in diffuse clouds. I mean, I didn't show in my talk, but I actually mapped in that same filament in Taurus methanol, and it's prevalent everywhere, even in the diffuse, in the filamentary structure, outside of the cores. And so methanol is very prevalent and is everywhere in the clouds. So it's a good question to try to pinpoint, timescales and how these things are being like reprocessed, right, in that like chemical evolution diagram.
Yeah, methanol is not really something we really think about much, I would say, in prebiotic chemistry. I guess
Mhm.
kind of under the assumption that it's probably not readily available, but if you, that's like one of the things you see the most, it's kind of interesting. So we have another question from Saritha Danthi. Does astrobiology need to be understood by reading books or research material for academians and scientific researchers? I guess is if I could rephrase the question, like, are there any
Mhm.
good layperson books that you could recommend?
Yeah, I mean, this is a great question too, because again, I think the last time I took a chemistry or biology class was like in high school, because my background is physics. So in undergrad, I was a physics major, and I actually did research, not anything like this. It was on like dark matter and galaxies. And so I kind of came into this subject with just, I mean, I had a good understanding of physics, and that helped, a good background, but I didn't know, I had to teach myself astrochemistry or astrobiology. I know that Chris Empey here at the University of Arizona has a lot of books, popular books about astrobiology, that people seem to like. It's a more popular, I think, science writing. But I think, astrobiology is such a broad subject that you can start from kind of any angle that you're interested in, whether it be astronomy or the biology route, which I know very, very little about. So, yeah.
Yeah, that's definitely true. Astrobiology is a huge encompassing field that you could, yeah, it's hard to wrap your mind around all of it for sure. So John Rosenfield asks, do you think that a percentage of Titan's COMs existed in the proto-moon stage? I guess like during the early formation of the solar system.
Yeah, I mean, sure, I think so, because in the protoplanetary disk phase, you're forming not just the planet, but the proto-moon itself. It's all within some, comes from the primordial clump. So I would imagine, just my guess, maybe, yeah.
Yeah, I don't know if you know, or maybe somebody in the audience knows, is the methane on Titan, is that the primary atmosphere, or did it evolve
Yeah,
later?
yeah. So I think it's the primary. Yeah, I'm not
Yeah,
a planetary science person, but I believe that's the case.
yeah. And so that methane would have just came from like the processes that you've been discussing today.
Yep. Yeah.
Yeah,
And actually,
very interesting.
there's people who do chemical modeling, right, of a collaborator of mine that looked at methyl form or vinyl cyanide in Titan's atmosphere, and it forms in a very similar, like the chemical codes that can reproduce the abundance in Titan's atmosphere are very similar to the processes that are needed to form it in the cold dense cores that I look at.
Right, interesting. Huh. All right. Well, if there are no further questions, I don't see anybody's hand raised. I guess we can go ahead and call it a wrap. So thank you again, Samantha, for the amazing talk, and thank you, Tim, for that wonderful introduction. So this is the last seminar of the year. And so we're going to start up again next year. Not exactly sure on the date when yet, but we'll keep you informed. So everybody have happy holidays. Yeah, and wish you well. See you next year.
Thank you. Thanks to the organizers again for letting me come and talk to you all.
Thanks, Albert.
Pleasure.
Thanks, Sam.
Thanks, Tim.